In the standard models of planetary science, a world's physical dimensions are largely locked in early. The professional consensus assumes that once a young star clears its protoplanetary disk, the surviving planets settle into a permanent size, with their mass and radius remaining effectively static. But a synthesis of modern orbital dynamics, isotopic records, and field theories suggests a different physical reality. Planets appear to undergo constant evolution, driven by a triad of forces: continuous external deposition, stochastic cosmic impacts, and internal mass generation. Tracking this evolution requires measuring the relentless microflux of orbital debris raining into the atmosphere, mapping the periodic catastrophic impact cycles dictated by the galaxy's gravitational tides, and examining theoretical frameworks of internal radial expansion. Examining a planet's true trajectory across geological time means investigating the specific mechanisms capable of altering its physical dimensions long after its initial formation. As the Earth orbits the Sun, it continually plows through a dense interplanetary dust cloud. Every year, the planet sweeps up between 40,000 and 78,000 metric tons of cosmic dust, micrometeorites, and cometary debris. This table breaks down the planet's net annual mass balance. While the Earth gains tens of thousands of tons of material from space, the solar wind simultaneously strips away approximately 96,000 tons of hydrogen and helium gas from the upper atmosphere. While this calculation results in a slight net mass deficit, the physical composition of the exchange dictates the planet's structural evolution. The mass lost to space consists of highly diffuse, unbonded atmospheric gases. The incoming material, however, is composed of heady, refractory silicates and metals that permanently integrate into the terrestrial crust. Aerospace operations have confirmed the exact origin of this incoming flux. When engineers recovered the Stardust return capsule in 2006, the samples proved that this material includes pristine interstellar dust. Even isolated in the vacuum of space, the Earth is an open system. Its solid surface is persistently seeded and augmented by baryonic matter harvested from the surrounding cosmos. This local harvesting operation extends beyond the immediate atmosphere. The Earth and the Moon function together as a highly interactive, coupled mass transfer network. Because the Moon lacks a protective atmosphere and possesses a weak gravitational field, it acts as an exposed impact sink. When kinetic projectiles strike the lunar surface, they shatter the regolith and launch vast quantities of crustal material outward, overcoming the Moon's low escape velocity. N-body simulations reveal exactly where that material goes. Once liberated, 22.6% of escaping ejecta is caught by Earth's gravity, eventually colliding with the planet. This capture follows a precise power law decay curve. Half of these impacts occur within 10,000 years after rejection. We can measure the results of this transfer physically. Catalogers have recovered thousands of these specific lunar meteorites across the globe, totaling a mass more than 5 times greater than all the rocks collected during the Apollo missions. The Moon orbits the Earth, but it also actively dredges the wider solar system for matter, functioning as an ongoing gravitational conveyor belt that reliably funnels mass to the terrestrial surface. While this constant dust and lunar debris provides a steady baseline of accretion, the planet's mass inventory experiences its most drastic revisions through violent, punctuated collisions. 66 million years ago, the Chicxulub impactor delivered roughly 16 quadrillion kilograms of rock and metal into the Earth's system in a single day. The resulting global atmospheric deposition left a permanent iridium-rich band in the geological strata, marking a massive, instantaneous injection of extraterrestrial mass. We have observed this mechanism operating elsewhere in the solar system. In 1994, comet Shoemaker-Levy 9 was ripped apart and absorbed by Jupiter. The resulting dark scars across the Jovian atmosphere demonstrate how massive planets sweep up orbital debris, acquiring volatile elements and bulk mass through energetic captures. These catastrophic mass injections are not statistically random. Their frequency is dictated by a macro-scale astrophysical clock. The solar system does not maintain a perfectly flat, stationary orbit around the galactic center. It oscillates vertically through the Milky Way's dense midplane every 30 to 40 million years. Crossing this galactic equator exerts a strong gravitational tide, severely perturbing the Oort Cloud. This alters angular momentum, triggering massive comet showers that plunge into the inner solar system. The rate of catastrophic mass addition to a planet is linked to the gravitational architecture and rhythmic cycles of the galaxy itself. Even after accounting for cosmic dust, the relentless lunar conveyors, and periodic galactic comet showers, standard accretion models leave deep anomalies unresolved. Current measurements show the Earth radiates 27 terawatts of internal heat that cannot be explained by radiogenic decay or primordial cooling. There is also a severe biomechanical discrepancy in the fossil record. Under the Earth's current worn gravitational field, the yield strength of bone is insufficient to support the dynamic loading of a 60-ton sauropod. The animals appear too massive for their own structural integrity. Resolving both the missing thermal flux and the biomechanical impossibility of the fossil record requires examining models where the planet produces mass internally. The chrono-genetic framework addresses these anomalies by proposing that planets are not formed from the bottom-up accretion of cold dust. Instead, they originate from stellar fission, where a parent star ejects a dense core to restore rotational equilibrium. In this model, the planet inherits a micro-singularity at its core. Chiral symmetry breaking at its event horizon allows for a process of endogenic mass generation, where vacuum energy is converted directly into baryonic matter. The predicted accretion luminosity from this internal mass creation precisely matches the Earth's 27 terawatt heat deficit, aligning the theory with observed surface temperatures. Generating physical matter from the inside out continually increases the planet's internal hydrostatic pressure. To accommodate this growing internal volume, the planet must undergo physical radial expansion. The Earth manages this without shattering due to continuous orbital dynamics. Immense gravitational stresses from the Moon and the Sun cyclically flex the planet, inducing fatigue and structurally weakening the rigid outer lithosphere. As internal pressure mounts, the fatigued crust fractures along active tectonic belts. Magma upwells to fill the void at mid-ocean ridges, driving seafloor spreading that directly increases the planet's physical radius. Scaling this expansion backwards resolves the Mesozoic paradox. Mathematical modeling yields a Jurassic-era Earth with a radius roughly 55% of its current size, creating a 0.76 G environment perfectly suited to the massive bone structures of sauropods. Seafloor spreading and tectonic activity are the active physical expressions of a planet continuously surging in both mass and volume. Planetary evolution is driven by a highly integrated network of forces. A planet's mass and radius increase through the steady orbital delivery of lunar material, the catastrophic mass injections of periodic galactic comet showers, and the internal pressures of endogenic matter generation. The model of a cooling, static rock, isolated in space, falls short of describing this reality. We reside on a dynamic structure, constantly kneaded by tidal forces, expanded by internal engines, and bombarded by extraterrestrial material. Planets are actively growing entities. Their physical dimensions and mass inventories are continually revised by internal quantum gravitational processes and the relentless mechanical rhythms of the cosmos.